remote so I can see the screen. Okay. So I think we are going to start at 9 o'clock. Before we get to the keynote, we have a quick chairs report and some information about the upcoming SPLASH in 25-26. So for this year, OOPSLA 2024, we were the PC, or as we are now known, review committee chairs. So my name is Alex and this is Evan. We had a lot of help because we had over 380 submissions in OOPSLA. And this is going up and up. Next year is actually looking even more at this point than this year. And as you can imagine, this is a big change from the traditional, 100-something submissions and in-person PC meetings. We had something called associate chairs, which is becoming common for all of the conferences. They're super helpful people. We had 2 rounds of reviews, so 2 chairs served for the first round, and then 5 chairs served for the second round, about 1:50 ratio. And they really, really helped us by looking after the discussions and making sure things go along. For these chairs, I think only Tobias and Anders are here. Are you here, Tobias? Anders? Yes, so this is Anders. So I'd like to thank those who are here for helping us run this, because basically it was a combined effort of the associate chairs and us to manage these huge numbers of submissions coming in. As for the review committee, as you can imagine, there is over 100 people, of which 98 were active reviewers. They each had to write around 5 reviews for the first round and about 10 reviews for the second round, but we tried to get it less, but it's hard. Committees are growing. The POPL, PLDI, ICFP, and OOPSLA all kind of compete with the same people, and they all have a lot of submissions, and this is getting much, much, much trickier to manage, and we really thank the program committee people who helped us. Again, is there anyone who is in program committee who is here who wants to sort of raise their hands or stand up? We can thank you too. Really? Okay. Oh, yay, Ben. Oh, yes, Ben. 2 Bens. More. Yay, thank you. So mostly they're here and they're helping with chairing sessions, and it's been enormously impossible job to do it with good quality reviews being written by these people. And as a result of this, we actually have paid attention. Later in the award ceremony, we are going to be awarding some distinguished reviewers for people who went above and beyond. And then along the distinguished paper awards, you'll see some distinguished reviewers who are here, hopefully come and pick up their award as well. Now, statistics, as is common in these kind of reports. As I said, we had 2 kinds of submissions. Some submissions are coming through from previous major revisions of OOPSLA. This is something we've done for the last couple of years, where you can get your submission not accepted, but with instructions on how to revise it, like you do in a journal when you come to the next round. So in that sense, when we had our first round, we had 103 completely new submissions, but we also, in addition to that, had 20 submissions that were major revisions of previously not accepted OOPSLA papers. So that's how we count 123 submissions together. And then similarly, in the second round, we had 249 fresh submissions, and then you had about 12 major revisions, many of them from actually the round 1 of this current OOPSLA who were not accepted in the first round. And then overall, we are around 33, 34 acceptance rate for our papers, which is actually in line around 30% for OOPSLA in the past, to be honest. We don't have any particular goal. We basically just, any paper that reviewers are very happy with and everyone is happy to accept goes in. We don't aim for like 5%, 50% or any kind of submission rate. That's basically how reviewers are. They try to be constructive and approach the papers with like, what can we do to make them work? The other thing that we used this year, as the numbers are growing, and it was used last year, is this Toronto paper munching system. Most places now started to use this. It's a very straightforward system, which is useful if you're a PC chair, that you upload the papers from the conference to this, it's a machine learning model, and you have every PC member upload their work and their papers, and it tries their best to match the background of the people who are reviewing papers with the papers submitted. And we don't just use that. We automate that initial step, so when reviewers have to rank the papers to pick to review, they're given to them in that order. So like, we think this is the best match, this is the next one, this is the next one. And then they go through that list, and they can stop at any point. They can go through all 300 papers if they want to. And they kind of say, oh, no, this one pull up, this one pull up, this one drop down. And then we allocate the reviews. And it's been much, much more useful as the numbers grow. So in other conferences, the numbers are even higher, and it just makes the whole work much easier. So the TPMS is what people talk about. So if you ever ask to review papers, and somebody asks you to upload your work to TPMS, please take it seriously, because the better the work it has, the better the matches you will get automatically by default, and the easier it is going to be for you to pick the papers to review. So, and it reuses that account across many conferences. So uploading it to TPMS once, if you review for POPL, PLDI, others, it will be all the same information. I'll pass it to Evan to talk about our rest of the processes.
All right. Okay, so for OOPSLA 2024, we had a revision of the terms of the categories. So as Alex was already alluding to, there's the accept category and the conditional accept category and the minor revision category, which are all different levels of we expect the paper to come in this round, in this version of OOPSLA. And then the major revision category, which is an instruction of like the paper perhaps needs a bit more time to be revised, to be submitted for the next round, but we want to have you come back and that you'll get the same reviewers and the same consistency of the criteria, and then the reject category. Now, one thing of a revision through the experience from OOPSLA 2024 was that to decouple the timing and the sort of minor and major revision aspects. So the 5 categories are going to remain for OOPSLA 2025, but the instructions on when to submit for this round or next round becomes a decision and choice of the authors. Okay. All right, and of course, that's the choice of OOPSLA 2025 about that, and the call for papers there. Okay. So here are the statistics based upon the authors, the country of authors of origin. So yeah, give a moment for everyone to look, but basically there's the US is still very US-centric heavy submission. China is pretty big, and then other countries, European countries and Asian countries at the top. Okay. Here's a word cloud to kind of understand where we're at in OOPSLA in terms of submissions versus accepted, and you can look for your favorite keywords and see whether it was harsh. Yes. Okay. And this is based on the title, and then I have one based upon the abstract. Okay, so no comment on particular what, but all right. And with that, really, and I couldn't appreciate the OOPSLA community enough for making this happen, the reviewers, the authors, and the submissions, and so forth. So, okay. Thank you. Thank you, everyone.
And now we are going to ask the 2025 chair to come up. So thank you, Evan. I'm now changing. I'm also Alex, who is the SPLASH Steering Committee Chair. and I would like to invite 2025 general chairs to tell us what happens. Okay.
Awesome. All right. Once again, thanks a lot, Evan, Alex. Amazing job. Great conference. Okay. Good morning, everyone. My name is Ilya. I am not a general chair for SPLASH 2025. So the general chair is Charles Zhang, who had to leave this morning, but he was here earlier. I'm a local chair, so let me tell you a little bit about where we are going to be and what the next year conference is going to be like. So probably many of you already know, so that the next year we are going to be in Singapore. So if you don't know where, okay, so actually, if you don't know where Singapore is, I'm going to show later, but what you might want to know about Singapore is that, well, typically that's the image that you see on the internet. This is actually what you see when you just land in Terminal 1 of Changi Airport, and then you take a walk, you see something like this, but there is much, much more to Singapore. It's a really, really interesting city. So you can go to Chinatown, see the old colonial architecture. It's really beautiful. Have a very very tasty and cheap snack. So you can go to Little India. It's famous by its unique vibe and murals. So you can get a durian, which is very popular and delicious in Singapore. Not far from where we are going to be, we have the iconic food court, hawker stalls, they call them in Singapore, called Lau Pasat. That's it. So you can also go to the city garden. You can actually, if you're into hikes, you can take a fairly long hike along the Makriche Reservoir. So that's it. If you come with the family, there's always stuff to do. Really beautiful aquarium. Or you can even go to the beach side. So if you want to prepare for your trip, well, okay, here's one piece of material I could find, but I'm not sure how adequate is it. Yeah, so again, if you're not sure where Singapore is, that's where it is. So as you can see, it's just slightly above the equator, so it's quite hot and quite humid, but well, as experience shows, people get used to it relatively fast. Okay, logistically, Singapore is very easy to get to, so there are direct flights from many major European, Asian, and North American cities. So these are just by Singapore Airlines. I'm quite sure the other flight companies provide even larger selections. Some people might need visa. So if you didn't need a visa to come to this Splash, well, there's a 100% chance you don't need a visa to come to Singapore. If you did need a visa, then the application process is super easy. It's online and it takes less than a week. So you don't need to go to an embassy or anything. Okay, so what else? So the public transport is very cheap, so you don't need to buy a ticket. You just bring the regular Visa or MasterCard or Union Pay card. You can also use taxis, so we don't have Uber or Lyft. We have Grab and Gojek, but they are nice and they are very cheap. And the city is very, very safe. So like, for example, if you want to go to a coffee shop, people typically book their tables by just placing their phone there and leaving to order a coffee. So that's how it works. All right, so I couldn't just skip that, so I want to say a couple of words about what you're going to eat. If you are into trying new things, Singapore is famous for its delicious food. So there is even a PhD comic about that specifically. If you are, so please come for science. If you are into fancy food, so also good news for you, but fancy doesn't mean expensive. For example, we have laksa stalls where you can get famous Singaporean soup just for less than $5 US. And it's actually, the queue is not forever, so you can come and you can get it. All right, so the venue, we are going to be in Marina Bay Sands Convention Center. So Marina Bay Sands is the only building people can imagine when you think about Singapore. But this is the hotel, and we are not going to be, this is not going to be the conference hotel, but yeah, for reasons that you might guess, but we are going to be in the convention center next to it, and it's right here. So from the inside, this is what it's going to look like. So one thing that I'm quite happy about, that this is going to be our hallway track. So I made this picture so we can see the whole bay, the Merline, the city. Quite a few hotel options around, so they are very easy to get to by metro or just by walking from the venue. So these are kind of like, this is what we have already pre-booked, but if you want to have cheaper options, there are plenty of cheaper options in Singapore too. Okay, so as announced, this is the organizing committee heads for OOPSLA 2025. Charles Zhang for Hong Kong University of Science and Technology is the general chair, so all questions for Splash specifically should go to him, and Shriram Krishnamurthy and Sukyong Ryu are the review committee chairs. So the round one submission phase has already passed. You probably know that, but don't worry, there is a second one later next year, so please submit to that one. And yeah, and that would be it, but I have another exciting piece of news that I'm going to share, because in 2025, for the first time in history, Splash will collocate with ICFP. So we will have two major PL events collocated together on the same week. So if you consider attend one, please consider attending another one. So this is the organizing committee. It's on the webpage, so if you Google for ICFP Splash, you will find these people easily. This is a very, very tentative schedule, so this has not been done in accordance, in consultation with the corresponding steering committee, so please don't angry tweet this picture if you don't find your favorite co-located event there. So what instead you should do is to keep the January 16th, the deadline in mind, and submit a proposal for a workshop and co-located event. And we very much hope that all the usual suspects like SAS and Prolala and DSL, they will be co-located again. All right, so since we are co-locating with ICFP, so these are the faces of ICFP. I'm actually the general chair of ICFP next year. And Dominique de Vrieze from K11 is the program committee chair. The submission dates are already up, so if you have something that has enough lambdas in it, so consider submitting to ICFP. All right, and this is all I have, so see you next year in Singapore.
And just to take one more minute of your time, we actually already know where 26 is going to be. So Anders is going to say a couple of words because he's the program chair for the 26 OOPSLA.
Yep, so OOPSLA is very well organized thanks to our wonderful steering committee. So we're already well into the planning of OOPSLA 2026 also. So in 26 we'll be back in California, more precisely Oakland, and OOPSLA 26 will be co-located with ISTA. Frank Tipp will be the general chair, and as Alex said, I'll be the review committee chair together with Nadia Polikapova. Thank you. So you can see a picture of the venue here in Oakland, so that's easy to reach from SFO, so it should all be easy for everybody to get there. So maybe it's a bit early to prepare your submissions already, but you can at least start looking forward to another great OOPSLA. Thank you.
All right, so that's it from us. Thank you. You can switch the laptop for Miacha. And just a quick note that if you are interested and you're on the East Coast or maybe Europe, or especially East Coast, in SPLASH or even SPLASH and ICFP in 27, 28, 29, 30, send me an email. We're always on the lookout for sort of a good place. Thank you very much.
Hi, everyone. So while we're setting up for the keynote, I had a couple of quick SPLASH 2024 related announcements. First, I think I was a bit unclear on the first day about what to do if you encounter a code of conduct violation. So it is true that no one from SIGPlan Cares is physically present here, but you can still report any code of conduct violation to me. So I'm the person to come to if you'd like to speak to in person about anything that you notice that you would like to report. Please come to me and talk to me. The second thing is that we had a slight scheduling change for today. We noticed that the underrepresented minorities lunch was conflicting with the awards lunch. So in order to deconflict that, we're going to do a URM coffee, and that's going to happen immediately after the keynote. So there's signs outside pointing you can grab some coffee and head over to the room. So we moved that event to deconflict that. Okay, so with that, I would like to introduce our keynote speaker, Neha Rangta. I'm really excited to hear this talk. So Neha's background, she did a PhD at Brigham Young University on the topic of testing of concurrent software. And then I first met Neha when she was a researcher at NASA Ames, and there she did a lot of really influential work on symbolic execution. If you've heard of the Java Pathfinder platform, which have been used by hundreds and hundreds of researchers, Neha was heavily involved in the development of that platform. And you know, very high stakes, right? We're talking about checking software running on spacecraft and this kind of thing. So really influential and important work. And then Neha went to Amazon, and there she and her team have just had an astounding impact. I think this is one of the best possible examples we can get of the real world impact that the work in our field of formal methods and programming languages can have in real world just enormous scale scenarios. So you may have heard about the Cedar language already this week with Amina Torlak's keynote. There's going to be another talk on that today. And that's just one of many products and services and systems that Neha's team has developed and invented and productized and made robust. So again, I couldn't be more excited to hear about more about this work and what goes into making this stuff real. So thank you so much.
For the kind introduction, and thank you very much for Evan and Alex to invite me for this keynote. I am super excited to be here and talk about essentially what Manu said, is scaling formal methods to the order of billions, trillions, and quadrillions. So as Manu said, I'm Neha. I'm a science director in Amazon working on a wide variety of things. And it's interesting that Manu said, hey, I finished my PhD, and that's after that he met me. And when I did finish my PhD, which was in 2009, if you had told me, hey, Neha, in a few years, you'll be at this stage at OOPSLA, at SPLASH, giving this talk about this scale of work, this scale of formal methods, I would have said, that's impossible. That's literally impossible. And the story I want to tell today is about making that impossible possible. So to begin this incredible story, we have to go back a little. And it begins with cloud computing. So a lot of you probably by now know what it is, but I'm still going to give a quick 30-second refresher on what is cloud computing. It's the on-demand delivery of IT resources via the internet, and you pay as you go. So you're not using anything. But in a more programming languages, because as we heard earlier today, everything's a program. So everything in the cloud is a program. Now, if you think about what the cloud does, is it gives you a function whose return type is a computer. Now, oftentimes we think of functions that return booleans or files or sockets, but now you have a function that returns a computer, which I think is pretty incredible. Because normally you think of computers that are on your desk, under your desk, in your data center, but we never thought of like a function that returns a computer. And you can invoke that function to get a bunch of other computers. It's not just a single computer. And what's more interesting is it provides you a way to program with that function. Everything's a program because that's what the cloud is. And imagine you're building an application that uses a database. When your utilization of that application gets high, you can shard part of that database and put it on this new computer. And when that utilization gets low, you can just go and release that computer. You don't need it anymore. Now, this helps you scale up and down organically. You don't have to think about how many computers do I need. And when the utilization drops, there is another function, F inverse, that allows you to release that computer. Now, with this, essentially these functions, imagine if you have a database that's also a function. And you can create your entire application with these sets of functions. The AWS console, it's essentially a web page. And that lists hundreds of services that are available to everybody. And they cover a wide range of use cases, including compute, developer tools, applications, integration, storage, media services, LLMs, databases. All of these are functions with very powerful return types. One example is what we call the Lambda service. That lets you run code without even managing any servers. So what you would do is you would call a function, which it'll create a server on your behalf. You can run your code, and then it destroys that server. Semantically, it is F inverse composed with your code, composed with F. And this is what we call serverless computing. Because here, even the server and the computer is completely abstracted away. When you get 1,000 requests in your application, 1,000 computers are created, used, and destroyed, all with an API, a single function call. And this is the kind of thing, what I feel is the impossible becoming possible. You now have computers and databases that are objects in your programming language. There's other functions here, reliable queuing, durable data store, fast key value pairs. All of these simple functions. who are using these functions? We have a broad set of customers across financial services, healthcare, telecom, satellites, public sector. They're all using these powerful functions to create and run critical workloads, store critical data. A natural question becomes, okay, you have all of these functions, but who is allowed to call these functions and when? Can an intern call F inverse on a database? Well, that depends. If it's on a production fleet, then no, you do not want that intern calling F inverse. But if it's on their own development environment, they're kicking the tires, they're trying to figure out what they want to do, learn about the system, then absolutely, it's a great thing that they can call F inverse on their database. The AWS Identity and Access Management System, IAM, is a common policy language that allows users of these functions to define who has access to what. And with the same policy language, users can control access to all the functions in AWS. And that is the genesis of our story. AWS has millions of customers. Each of the customers have hundreds and thousands of policies. And that is why we have been able to scale formal methods, automated reasoning, to billions of SMT queries, to trillions of verified policy evaluation, and to over a quadrillion policy validation. Now, by providing analysis capabilities to the policies that the users are writing, we got to billions, not the TV show, but the number of SMT queries that we generate a day. As part of this journey, in 2022, I gave a keynote at CAB where we talked about generating 1 billion SMT queries a day. For that, we built a policy analysis tool to reason about the semantics of AWS access control. The tool called Zelkova would translate these policies into SMT formulas and then try to prove security properties. And a little bit on how this works, the details are, you can go, it's on YouTube, you can go watch the talk. But it uses a portfolio solving approach. So Zelkova calls a set of SMT solvers in the back end and returns the result when the first one comes back with an answer. It's a winner-take-all strategy. And this actually helped us, allowed us to leverage the diversity in the solvers that we have and quickly solve queries, because here we are doing it for safety-critical systems. Now, with these use cases, we were at 1 billion SMT queries in 2022 when I gave that talk. And you know, Manu quite aptly recognized when, in my previous life in my research, a few hundred was a big deal, which was like, that was considered influential and considered a big deal. But now we got to 1 billion. And it seemed like, is this the limit of what we can do? In fact, after my CAV keynote, I got a question. What's left to do? Aren't we there? Aren't we at the epitome of what's possible? And at that moment, I knew, and I said to them, this is the beginning, not the end, which was a huge difference from when I'd finished my PhD, where I thought today was impossible. Now I know we are just getting started. And I hope by the end of this talk, I'm able to convince you that we are just getting started. I want to give a quick taste. I'm going to talk a lot about IAM policies today because that's the context of the work that I'm going to be presenting today. So here's what IAM policy looks like. It has an allow statement. It has a deny statement. And the basic semantics of the policy is that access is denied by default. If there's no policy, access is denied. Nothing can happen. To grant access, you have to have at least one allow statement. You actually have to say that Evan has access to this resource, an explicit allow statement. And there should be no explicit deny statement that matches it. You can say, oh, everybody at this conference has access to this, except we're not going to give Manu access because we don't trust him with the system. You know, it may be very well be the case. So here's why an explicit deny statement could work out. I call it an expressive-ish enough language. That's my super technical term for it, because it has string matching operators, with negation, and wildcards. I know, it's starting to get, you get the sense of why I'm calling it expressive-ish enough. So what does the policy do here? Here the policy states that users can perform all EC2 actions. EC2 is this computer service. It's the thing that gives you computers. When you call, there's multiple things you can do on it. You can run workloads, you can start things. So the policy is saying the user can perform all the actions for EC2, the service, but cannot start instances outside the US. So it means it cannot get a computer that is stored outside the US. And you can imagine there is a regulation where certain data, certain workloads have to stay within certain geographical boundaries for different reasons. And here's a way you could encode your requirements, your business needs into an access control policy language. And here is what the translation to SMT looks like. If you spend like a couple minutes, it's actually a very straightforward translation. The details here don't matter, but we define the variables that are found in the policy and are asserting that any request that matches the allow and does not match the condition for the deny statements. And you can then prove multiple things about this policy. So it looks straightforward, right? So how did we get to 1 billion SMT queries from this very straightforward encoding? It was the use cases. It's given that we have millions of AWS customers and hundreds and thousands of policies that each of these customers and each of these accounts are having, they wanted to have control and visibility. So now that the fact that your computer is not at your desk, not under your desk, or not within the physical confines of your data center, it's over the internet. You're calling functions to get access to it. So access controls become super important. And the variety of use cases were preventative, ensure no matter what, that the data store that has my data is not accessible to the internet. You don't want any arbitrary person being able to access my critical data. But they want it to be preventative. They never, ever want to create a resource that would grant such access. You want detective controls. Oh, something happened. I can look at that event and say, I don't think I want that to happen, but I want to be able to detect for anti-patterns to ever see in that large ecosystem that something bad happened. Then there's proactive. In a lot of development environment, you want to check for best practices before you deploy your access control policies, either in the CI/CD pipeline or in the versioning system. It's all within part of your development ecosystem. So we published a paper in 2018, I believe, in FMCAD about how we do the encoding for Zelkova. There are some interesting use cases because I said it's an expressive-ish enough language where getting the encoding right and getting it to scale, there's enough interesting things. One of the very first use cases we built was integrated Zelkova in a service called AWS Config, where we had the users building check built on top of Zelkova, and it wanted to do automatic detection of when you go from a version of a policy 1 to a version of a policy 2, did the permissions increase? Because if it increased, there may be a risk of privilege escalation or you're giving more permissions than you require. And these are the types of checks that customers could just integrate in their CI/CD pipelines. It was a very powerful capability. We kept going from there. We went from the CI/CD pipeline world to a preventative world. So this paper, which we published at FSC, is about S3 block public access. Here, I believe this was a watershed moment for formal methods. We integrated a formal methods tool an SMT solver in the request path of a high availability, low latency service. It was a tier 1 data service. So how did we do it? The one answer is very, very carefully. The other answer is we said, what's the one thing that, one property that nobody wants? Nobody wants their data to be public unless you're hosting a public website. Other than that, why would you want arbitrary people to have access to your data? So this was a global property that we figured out how to do it. And again, there's nuances. What is public? Are people in this room the public? Are people in Pasadena the public? So that was our challenges of how to figure out how we did the specification. So please go read the paper if you're interested on how we came up with saying what is the public. And the reason this became the watershed moment is often formal methods is thought of as a nice to have. Like, oh, we can raise the correctness bar. Here's the designers are doing something in hardware, but then you'll have the verification engineers doing the verification in software. It's like, okay, we'll find these bugs, and if we find the bugs, it'll do better, or we'll do better test generation or prove parts of it. But here, this was integrated as a security guardrail in a core service. It was part of the computing fabric. It turned from a nice to have to a must have. It didn't depend on the 3 engineers who were going to work on it. Even if they left, the folks running the service were going to be like, okay, how do we find the next 3 people who are going to be able to run and maintain this? Because it's something that we're providing to customers. Now, as we went on, we said, okay, why is this so important? S3 is the data store service that we added it for, and it serves millions of customers for all sizes, industries, where they store, manage, analyze, protect large amounts of data. And it supports virtually all use cases: data lakes, cloud-native applications, Gen AI data, mobile application. And with this, we were able to provide the users the highest level of confidence in their security. Things we used to say for aerospace, things we used to say for embedded systems, things we used to say for safety critical systems was now part of the cloud computing fabric. Okay, we kept on going. This is one spec. What more can we do? At the end of 2019, we launched an AWS service called IAM Access Analyzer. And here, it uses predicate abstraction to help users that access control. But it's not a single thing. One of the challenges we had faced was most use of tools, formal methods tool. A user has to put in a lot of work to figure out what's the specification. For block public access, we figured it out. We spent a ton of time to say, what's the specification, what is public? And then customers could just turn it on, one click. So it requires serious expertise, a lot of time, and often that becomes the blocker or the barrier to adoption of a formal methods tool. And so what we did with Access Analyzer is we moved away from it. The goal is the machine does all the work. The machine infers the specification, and then the user layers their intent on top of it. So the workflow here was this: users start with a service, they review their findings, and then they take action. And what's happening is the users are telling us their specification interactively. And this is a key part, by the way, to how we got to 1 billion as well. What happens when we generate a finding? When we say, if Bob has access to something within my account, okay, we'll go and analyze the policies in that account. It'll create a bunch of SMT queries to say, okay, yes, Bob has access, and Alex has access, and Alice has access. That happens. But it's not a static environment. Things are constantly changing. Developers are doing things, creating resources, creating policies. So based on those changes, there is a change event log that gets generated in this cloud environment. It's another function. It's a logging function. And based on that event, the analysis says, should I rerun? Because now, previously Bob used to have access, but now based on this event, Bob and Alice both might have access. So based on this change event, it runs the analysis again. So that leads to more SMT queries. These event logs can be a bit flaky, can sometimes get lost, sometimes get out of order. That can impact the soundness of our analysis. So how do we build a guardrail to protect for that? We build something, it's called an anti-entropy scan. What it does is every 24 hours, it does the entire analysis the way it did when you first turned it on. And this ensures any event that may have gotten reordered or dropped, no matter how small, eventually gets caught up. The system gets caught up and your analysis is complete. That leads to a whole bunch of other SMT queries. So now you can imagine with large customers, with many things, as they're doing it, this gets us to 1 billion queries. And this is not the end. We are continuously working to improve it. Earlier this week, you saw a talk by Changha on how we are actually now saying, based on logs, we can say, here's how you refine the policy. Here's how you remove permissions for somebody who's not even using it. Because maybe you had a developer who needed it, this permission 2 years ago. Now they don't need it, but as most things, you don't remember that I should go and fix it. But now, if you haven't used it, you can look at the policy refiner work that Changha presented on saying, oh, here's a recommendation for a policy that can just remove this unused action. Okay, so now we're done. We're at the 1 billion SMT queries. We are at a fork in the road. Where do we go from here? Do we declare victory on IAM? We've gotten to 1 billion. We've gotten to a place where no formal methods tool had gotten to before. Or do we double down on it? Continue, right? And the answer is we did both. You heard from Amina earlier this week on Cedar. You're going to hear from Craig later today on how he's going to talk about, we developed the Cedar policy language, which is for everybody who's not an AWS service. And I am going to keep talking about, for the rest of the talk, on how we kept going down the IAM path. That is where we get into trillions. We verified the engine that evaluates the IAM policy. I've been talking about symbolic reasoning of the policies that customer generates so far. Here, it's about the engine that runs in AWS, that when a customer makes a request, evaluates the request to say, should you have access or not. All requests made to AWS go through that engine. Every single request. And we verified that engine. So here's how it works. The end users define policies, as we've talked about, on who can access what, who can delete this database, who can create it, who can put things on it. And again, it's a single policy language across 200 services. To perform some action on this resource, such as a write to a database, the user makes a request. And the authorization engine evaluates, given the policy, whether this request should be allowed or denied. This authorization engine is called 1 billion times a second. This is actually an outdated number. It's now called 2 billion times a second, but the official updated number is 1 billion times a second. So let's imagine it's still 1 billion times a second. And if we do the math, it adds up to 86.4 trillion times a day. We come to the natural question. Okay, we want to prove that the policies being evaluated are correctly being evaluated. How do we go about doing it? We have I would say, a notion or a standardized process of how we would want to do it. It looks straightforward in theory. And in practice, I'm going to tell you about how we had to innovate across multiple dimensions. There was nothing we could just use out of the box. And trust me, we tried and looked. The engine that we wanted to verify is implemented in Java. It's historically done in Java. It's Java. So like, OK, what are some Java verification tools we had? We thought about using something like OpenGML or Key. What we realized as we did some experiment is these systems really struggled with complex Java features like exception handling, mutable state, heap manipulation, and the amount of work that would have taken to extend those tools or build a new tool would have just been too much. So we kept looking. I'll come back to what we actually used. And in the process, the other problem is there is a very clear divide between what we can model and what's the real world. And I've already given you a hint. At trillions a day, the reality is very, very real. It's more real than what we could have imagined or dreamed of. Let's just say that. But that's for later. That's hard. So let's start in the model land, where we've seen this before. We've seen this story. We've seen examples of this. So the first step in our journey is to prove correctness of the IAM authorization. What do we need? We need a formal spec of what the IAM authorization does. Now, it's an existing system, right? So, OK, we can take elements of its design. We can take the history. We can look at code. And we can formalize it. If you're starting from a new system, the specification is written up front. But given that we are verifying an existing system, we have to take the specification of what the system already does. As I talk, we have a rich set of resources. We have public documentation. We have code. We have comments of code. We have people who've worked on this system for multiple years. So we start looking at the documentation, and it turns out the spec is there. Even though it's not formalized, the spec is very clear in most cases. One thing is deny by default. If there is no policy specified, access is not granted. And it creates a very good secure by default security property, because that's the kind of thing you need in a system where it's like, if I didn't say anything, nothing's going to happen. I know that for sure. OK, we continue. Explicit allow statements override this default deny. If everything's denied all the time, it's going to be a perfectly safe system, but not very usable. In aviation, we had said a plane that's perfectly safe is the one that never flies. You just cannot ever happen. But that's not a very useful example. So what this is saying is, if you have a clean slate, you have nothing defined, you write an allow statement that says, oh, Bob has access. You've very explicitly done something to grant access. And finally, you have an explicit deny that will override any allow statement. And this is actually a powerful property. When you see a deny statement, you know access will be denied. You're not worried about, oh, is there another allow statement earlier or later that can ensure that this is not going to happen. So we're going to dig into this theorem. They didn't call it a theorem, but it is a theorem, that deny trumps allow. If we write it out a little, it's saying for any policy set and request, if there is a statement S in policy P, that's effect is a deny, and the statement matches the request, then when you evaluate the request, access is denied. You could take that simple property that we saw, the one-liner, and write it in a pseudocode manner. Well, how did we implement the specification? We implemented the formal spec in Dafny. We chose Dafny because it came with a built-in verifier to define the specification, prove the theorems, and moreover, Dafny had very Java-like declarations. It had variable assignments, loops, classes, inheritance, and it also supported functional features like algebraic data types, mathematical sets, maps. And a way to think about Dafny specifications are, for any of you who are working in IFO, like code contracts in IFO, it's very similar to that. They have, it has pre and post conditions for your methods as well as your loops. And a Dafny verifier uses an SMT solver in the backend for proof obligations. And finally, Dafny can also compile the verified code into various target languages. So for all of these reasons, we were like, okay, we're going to go and use Dafny. So the way you would have it is in Dafny, you can write explicit lemma about which pre and post condition pairs represent an implication about the inputs. So we talked about, here's the policy at the request, and if the requires is this conditions clause, it says if, essentially it's the same thing that we said, if the policy P matches a statement in S where the effect is a deny and it matches, then the ensures clause says that when you evaluate the policy and the request, it's a deny. Simple enough lemma, right? Okay, but Dafny doesn't know what is evaluate. Okay, it doesn't know what evaluate is. We can tell. We can inform Dafny about what evaluate is. We can write a specification for evaluate. And I want you to forget about performance and efficiency for a little bit. We will come to it, I promise. But just imagine we are in a world where performance and efficiency doesn't matter. It does, but just not for the next 10 minutes. So the way we do is we write a Dafny function. And the keyword function tells Dafny that this is a specification. We give it a name. Evaluate seems perfectly fine. That's what we'd called it in the other thing. It takes as arguments the policies and requests, and it gives an answer. The three things that we care about: allow, explicit deny, or an implicit deny. It searches through all the statements. If it finds a deny, explicit deny statement, then it returns explicit deny. If it didn't find the deny statement, it starts looking for allow statements. Does it match an allow statement? If it found an allow statement, then it returns. And if it's done, didn't find a deny or an allow statement, then it's implicitly denied. But there's more layers to the specification. So you can have an evaluate, which matches the deny statement, which will have a matching statement, which will have a condition. And a possible condition is string equals ignore case. So let's go through this whole cycle with one of the specs at the very bottom with the string equals ignore case. And for that, we need to look at the specification of case-insensitive string equality, or in other words, case-insensitive string equality. Now, the reason this is an important feature is because certain policy language features depend on it. The identifier for a subnet, which represent a range of IP addresses in your virtual network, is case insensitive. This virtual network is very similar to the type of networks that Todd was talking about earlier, but this is virtualized version of it. Todd was talking about real networks where the packets were passing through. Here, it's a software version. It's a virtualized version. And then we can also have things like tags that are added to resources. You can add a tag to a database that says production, and you can say anything tagged production, an intern cannot delete. That's how you can use these tags. And tags are also case insensitive. And they are implemented using the string equals ignore case operator. What does it mean? What does string equality mean in this case? So let's look at the documentation. It says exact matching, ignoring case. That sounds easy, We'll just ignore the case. So easy. What's the hard part? And I'll beat the dead horse a little bit. Here's how easy it is. Splash is splash. Splash is still splash. Splash continues to be splash. But splash is not OOPSLA. Okay? But life has a way of making things interesting. It always does. I can hear the Germans or the people who know Germans laughing at this. The letter on the one side you see is the German S, also known as a sharp S or the SZ. It's equal to SS when comparing things case insensitively. What makes it interesting is the sharp S is one character, but SS is 2 characters. That's not all. The Greeks have their own thing. The capital sigma is a different lowercase sigma if it's in the middle of the word or at the end of the word. Okay, you're thinking, why are we talking about this? Haven't we solved this problem already? Like, this is languages. We've been doing this way longer than computer science. You're right. We have. We have the Unicode standards. But I have good news and bad news. The good news is it does have all the answers. The bad news is it has all the answers. 1,140 pages of the answers. You can go to page 296, section 5.18.4, where there is a description of caseless matching. And it describes it in doing it in terms of something called case folding. Intuitively, you can think of it as lowercasing, but a few small deviations to make it work right for caseless matching. Now, there's about 300 out of 150,000 characters that are different for their lowercase. Okay, now we know what to do. Let's go back to Dafny and write the Dafny specification for string equals ignore case using that Unicode spec. The Unicode spec tells us to do it using case folding, and we can go read the documentation and then write that logic in Dafny. Okay, but how do we know we got it right? We can go read it, we can go write it. We are a human writing a spec, and we can make a mistake in writing and understanding. Generative AI is all the rage. You can have your favorite LLM generate the spec, but that may hallucinate. So how do we know the specification is right? We go to our next version in this next phase in our cycle. We prove theorems about the spec. We prove that we actually got it right. And this is not the most easy step anyways. This also requires understanding of the types of things you'd want to prove, the types of things that actually make sense proving it. So we think hard and come up with a list of things we want to prove. One easy one, transitivity. Strings should be transitive. Is A is equal to B and B is equal to C, then A should be equal to C. And if that's not the case, then we've made a mistake in writing down the spec. Okay, let's start that. Let's start that in Dafny. We say for all strings, A, B, and C, if A and B and C are related, then A and C are related. Dafny can actually prove this without any help. This theory is relatively simple. And this is another reason we ended up using Dafny. Dafny did provide a lot of automation. For simple theorems, it can just go and automatically prove it. You can think of this as a basic sanity check. I call it a unit test. This is the unit test of whether our spec is correct or not. And the more automation you have, the better, because remember, this is like the tiny leaf of this bigger authorization program that we need to prove, algorithm that we need to prove. So what else? We can say, okay, actually the Unicode spec tells us that if you lowercase 2 strings and they are equal, they should be equal even when you case fold them. That's a nice property, a little bit harder than the transitivity one. We're like, okay, we can do this in Dafny too. For all strings A and B, if you lowercase a is equal to lowercase b, then A is equal to B. This is not completely automated, but with a little bit of work, we can actually prove this in Dafny. The nice property about Dafny is if we had messed up and gotten the implication wrong, we wouldn't have been able to prove the theorem. And in that sense, it provides a guardrail to ensure that the spec is what you intended. Okay, now we have some confidence that our spec is correct. It's doing what we thought it's doing. We have theorems, we have confidence, but are we 100% sure that our spec is right? Probably not, because confidence doesn't mean completeness. So we'll say, okay, let's implement it, because that'll give us another way to do it. It's something we can execute. Specs are for humans, and implementation is for the machines. The nice thing, we can start this implementation in Dafny. We don't have a different specification language and a different implementation language. Calling it a method in Dafny indicates that this is the implementation, and it's something that we are going to execute. But one other bit, we need to connect the implementation to the specification. And we do it using the ensures clause. Now, we name the result of the method call and tell Dafny, can you pretty please prove that the result is equal to the specification? Dafny's like, okay, cool, I'll do that. Easy peasy. Because it's a simple theorem. For all strings S1 and S2, the result of the method is equal to the result of the specification. The reason Dafny has no trouble proving this is because they're literally identical. And remember the time I said, like, let's not talk about performance, but now we're going to talk about performance. We cannot run this implementation on an engine that's called trillions of times a day. The trillions kind of makes performance important. So what do we know? We know most strings in the world are not equal. Splash and OOPSLA are not equal. If you take two random strings in the world, they're not going to be equal. So what the current implementation is doing is it takes one string, makes a copy, takes the other string, makes a copy, then starts to look at the first character. It's like, oh, the string splash, S, is not equal to the first character of the string OOPSLA. This is very expensive. Your garbage collector will have to come run on and like take care of all these things, all the allocations you made. So frivolous of us to make all of those allocations. But that was an opening salvo. Clearly we can do better. We're smart people. We don't need to allocate both strings. Let's just walk the string character by character. Let's try and see what happens. And we have the ensures clause watching our every step, making sure that we don't make a mistake. We're starting in round 2. We say, let's check if the lengths are not the same. If they're not the same, we'll return false. If the lengths are the same, let's start walking character by character. If they differ only in the interesting characters, then we case fold. And if not, we've made it all the way, they're equal. This is great, simple, fast. Not quite. Dafny won't come out and tell you what went wrong, just so you know. But you can dig into the proof a little bit, and it's because of that case folding, certain characters can lead to different lengths. But the nice thing is Dafny tells you, look, your algorithm doesn't work. This implementation doesn't actually work. We're not people to give up. Let's try another implementation. We'll improve the previous one, and we'll have our friendly neighborhood Dafny ensures clause keeping an eye on our every move. The Unicode standard says only 300 characters out of 150,000 need special attention. So let's look for those first. We can walk both strings to see if we see something out of the ordinary. If we encounter one of the 300, then we do the slow implementation with all the allocation and everything. and the fast one on all the others. Dafny was like, great job, you got it right. And the question is, are we done? Can we do better? A system at this scale, you start to care about tail latency. Things at the end, you really care about it because you're still scanning entire strings. It's too eager. Can we be a bit lazier? Okay, we love lazy evaluation. It's my favorite kind of evaluation. So let's lazily look for unusual characters. We're going to use a pointer, but remember we allow for strings of different lengths to be equal. And we want to be a good citizen, not overrun the lists. Technically, the ensures clause in Dafny is keeping a watch, but we as programmers have our own pride. So we find the list with the smaller length. We go character by character, looking for the 1 in 300. If we find one of those, we do the slow thing. If not, we continue. If they're not equal, we return false. Or if we make it to the end, we went from a one-liner to this much bigger implementation for just one of the leaves of our implementation. We returned. And Dafny proves it correct. But for this simple leaf specification, the code has become much more efficient, but far more complex. In the first version, you can look at it and be like, yes, it's right. In here, you're not so sure. Like, even the best of programmers would have to spend a bit of time, convince ourselves, do some test cases, really try to see, like, am I right? Is it not? And the proofs really help ensure that literally that we are not making mistakes. But remember this no free lunch thing that always comes in the way. Why can't we just do it all? Proof brittleness. Proof tools are temperamental. So for folks who've not worked with Dafny, it relies on multiple pieces of software working together. The Dafny implementation consists of a large collection of axioms about the behaviors of the data structures like sequences and arrays, a compiler to the Boogie intermediate language. It uses the Boogie implementation and then uses Boogie lib to SMT. And it relies on Z3, the Z3 SMT solver to discharge each verification condition. For anybody who's worked with any of these tools, changes to any software artifacts can change how much verification effort it requires. And it's hard to predict whether each verification run will succeed within a reasonable amount of allocated time. And it can happen due to many things. Random search choices in Z3 during proof search, or whether you can have some naming differences of how your SMT lib file was generated. And even if you're not changing the Dafny program, a syntactic change to your Dafny program can impact massively the resource requirements of a seemingly unrelated changes to the program. I've seen it happen even if it's a semantically like no-op. Like you change something that's just a syntactic change, but not a semantic change, the resource counts can go up through the roof. We call this proof brittleness. Now, the reason this is important is in our system, proofs are not a one-off thing. You're not like, oh, I went there and did this proof and now we're done. No, it's a continuous evolving thing. It's an organism. It has to live and breathe and requires feed and caring. It has to be maintained and updated. So one of the things we had to do, this innovation we had to do was provide a way to control brittleness. And we did this by using the resource count provided by the solver. In principle, proof brittleness can be avoided by what we call a verification resource conscious style of programming. Like if you're a programmer and you do something, you're very aware of the complexity of the algorithm that you're writing. You're very aware. You have your big O notation going in your head. And it's the same thing here. You need to have a resource count in your head when you're developing the proofs. So we identified a system of using Dafny, which we call Dafny'24. It carefully avoids Dafny features that result in brittle verification conditions. And we had to rewrite large parts of our Dafny code to follow this style, because upgrading to Dafny would take days, or making a simple change would suddenly cause proof tools to time out, huge things. So this was a key thing we had to do. So like, how do we ensure that with every change, our proofs are not timing out? And after that, we realized our rewritten code required massively fewer resources and a much more stable behavior with updates. Okay, now that we have a verified implementation, can we just go ahead and run it? Not quite. We cannot take the Dafny code and just run it. This is an authorization system that runs across 1 million hosts in AWS, across all AWS services, called trillions of times a day. And this engine lives in an ecosystem of other dependencies, other tools, other libraries. And Java is actually very widely used at Amazon for a lot of things. And for us, we can't say, oh, go change your complete runtime and now use the Dafny runtime, because that's going to give you what? That would be a 10-year migration if we had to say we had to do it. So that was just not feasible. So based on that, we decided to generate Java code from our Dafny model. And if you remember earlier, I said, OK, Dafny does generate code that can be run on multiple target environments. So how did we do? So for that, we had to know, what are our requirements? What do we want from a compiler? We want it to be fast, and we want it to be correct. OK, that's good. But what else did we want? We added a new constraint. We said we wanted it to be readable. We wanted the code generated to be readable by humans. Generating code that machines can read is the easy bit. The reason for that was the authorization experts were Java programmers. And the ability to read code could help them understand, help us understand, are we doing it right? It would allow us to plug into an important existing development process, the code reviews. Now, as I said, the authorization experts are not Dafny programmers. So for them to just learn the logic, learn Dafny, would have taken a long amount of time. The ramp would have become a bottleneck. So generating idiomatic code, what I call is like not just readable. Humans are resilient. We can read, if you're John Reger, you can read LLVM code in your sleep. But part of it is, can you generate idiomatic code? Debugging was another reason. Readability becomes very helpful for debuggability. If you're seeing unexpected behavior in the generated code, you can step through the code, and then you know whether it's assembly versus a higher level language. It's much easier to debug code that is readable. So the built-in Dafny compiler met the first two requirements, fast and correct. With the readability, it was not even in the race. And as we were starting to look for, you can look at here the output generated by the Dafny compiler. You don't have to understand the specifics here, but it translates types of things that are non-ideal when you're interfacing with other code. So here, rather than a Dafny sequence of code point, which is what the compiler generates, it would have been great to have a string here. People understand strings. Another small piece of Dafny code that calculates the smallest length of two lists. The Java code that we want to generate, that we want it to look like, is this. But the Java code that generates is this. So we created a custom compiler for a subset of Dafny that generates idiomatic readable code. Now, there's certain limitations to this. We don't do it for all of Dafny. It's a very curated set of Dafny where some restrictions are the result typed expressions are restricted to either a return position or the pattern matching position. And this allowed us to mimic the Java's behavior on exception handling and try-catch constructs. We do it with 30 self-contained type-preserving transformation passes. So things like shortening the identifier paths allowed us to, again, create more idiomatic Java code rather than just saying it is Java code that runs. Now, this is the output that our Dafny Lite compiler generates for Java. You see Dafny, and then you see the Java. And there's a pretty good, beautiful, logical connection between the two codes. So you look at the Dafny, you look at the Java code, and you're like, I see how they are connected. And it's idiomatic to a Java developer. To give you a sense of the size, it wasn't big. Like in terms of just the lines of code, it's not big. But it was tricky. It was about getting that your specs are right, your implementation is right. And you can see the development size is really dominated by the specs and the proof. The actual engine, both on the Dafny side and the generated Java side, is pretty small. So after all of this, you're coming up with an artifact that is very manageable. It's very maintainable. OK, we have an executable spec, but we got to validate it. There's lots of things we can do. We know how to validate whether our implementation is doing the right thing. We have unit testing. We have fuzzing, like we do for all pieces of code. There's advantages. Like this is the real world people have a lot of experience with. We have industry standards. The Unicode committee actually publishes test cases for the folding. Python has a nice Unicode library, so we can fuzz our implementation against the Python one and make sure there's no difference. And if that gives us a difference, we know we're wrong because Python has been doing it for a lot longer. So when that happens, we restart the cycle. We fix our specification. We go all the way. We make sure the theorems still hold. If they're not, then the spec's broken again. We need to go fix it. We do the cycle. Hope we regenerate the thing. We test our implementation. We generate the implementation. We iterate. And we do it until the software engineering development lifecycle is similar to the proof engineering development lifecycle. But remember, we're still at this bottom piece of authorization. We're going to essentially have to work our way up. From every leaf, we're going to keep working up, match the conditions, match the statements. We come to the deny, come to the evaluate. So based on this one example that I provided, you can imagine, right? Like it grows in complexity. It won't fit on the screen. But you can imagine us going through that process. But I want to talk about this, right? Like I said, the reality is more real than one can have imagined or dreamed of. So how do we really know that we are connecting reality to the model? We've done testing. We're good citizens. We've done the effort. And this is an authorization algorithm that's called trillions of times a day. How do we do it? How do we bridge this divide? The answer, to get the confidence in trillions, we had to go to quadrillions. And this is a very, very true story. So we leaned into the fact that the old Java code that's been running in production happily for 15 years, and we've inferred our Dafny spec, we've read the documentation, we've created a Dafny implementation. We also have a new Java implementation. But what's missing is the connection between two pieces of Java code. We've been doing connections in all different places. There's nothing concrete here. The old Java code, let me tell you, looks nothing like the new Java code that we generate. You can't just look at the two and say, are they equal? There's no logical connection. We can't just lob the new Java code in production. We have no idea if it's different or not. What are we going to do? We've done those things, unit testing. Again, the same things, unit testing, fuzzing. But what happens when the moon's on the other side? We don't know. For that, the fact that authorization is already massively scaled, we implemented something called shadow mode. How does shadow mode work? It's very simple. The customer sends a request. You run the old engine, the existing one that's been running for 15 years, and you send back the answer. For the customer, if it's an allow, it's business as usual. If it's a deny, then it's a deny. But at the same time, you call the shadow engine. You do the exact same thing and run this new engine. And if there is a mismatch, you log it. Or you can log other things. If the new code is super slow compared to the old code, you can log it. You can think of anything that you can think of, and you can log it. You have metrics. As we were building this, my lead scientist on this project came to me and said, Neha, we've done a really good job. The team has, we have. We're very bullish. We'll probably see maybe a few differences. It's a big system, so maybe 100 a day, but we've done a good job. Like, okay, sounds fantastic. Let's rock and roll, see where we are. And we did. There's around 100 million mismatches per day. Now, you can be like, oh my gosh, this is surprising. Wow, that's a large number. But think of the percentage. It's a very small percentage at this scale. So how do you debug 100 million mismatches? Well, in the same way you would debug 10 mismatches. You go look at them one by one and figure out what the difference is, knock one by one. And the hypothesis is if you find one, you're going to eliminate a class of mismatches. It's not like you have 100 million unique mismatches. I want to give you a taste of a mismatch that we found. The shadow mode, this is something the shadow mode found that we didn't find any other way. So there is a notion of time in IAM policies. It can allow you to say, I only want to grant access to the OOPSLA attendees for this amount of time. So it has this notion of time. You can write down the date and time. It even goes down to the milliseconds. And the standard actually even allows for microseconds. But there are two different formats of times. You have epoch time, which is second, which we used till 1970. But you have the ISO 8601, which is the time standard. And there's one thing interesting here is if this is the kind of code we have, it's abstracted away, but this is the type of time handling. There were some data types that were millisecond precision, some that were second, some that were Unix or epoch, and there was numbers that nobody in the team could keep their head straight about what is it and what's a safe assumption or not. And one of the notions, like the science, like, can we just simplify it? Can we just make it all seconds? Because one of the things is IAM is a large distributed system in the back end. When a customer creates a policy, it takes a while for it to propagate along the control plane, get copied along all the different hosts. So that takes a few seconds. It's not instantaneous. Now, clearly, there's something wrong with our assumptions because I'm telling you the story, which means there was a bug. The idea was there's something called session policies that get inserted in credentials. And what customers were doing was using that feature to test the date time. What they would do is create a policy and say, half a second later, deny me access. Then try and test it whether access was really denied. It was no real world use case. They were just test cases that a bunch of customers had turned on. And that led to mismatches. Okay, great, we found it. But remember, we added the millisecond back, fixed the spec, reproved the theorem, fixed the implementation to match the spec, run the compiler, create the shadow, you see that process. And then we're ready to hit the road again. Okay, good news. We got lower, but it's not there yet. Now you can see a ramp up time. Like you see, like there's a ramp up time and then it stabilizes. That's because this algorithm's getting pushed to 1 million hosts across. So the deployment itself takes time. So as the engines are picking up the deployment, you start to see it. We found we kept finding the problems, right? Like month after one, we kept ratcheting it down. There was a Unicode problem, a couple other problems. But the process is long because the whole cycle has to repeat. And it took us a quadrillion samples to get there. It took us a quadrillion samples to say, are we the same? Are we there yet? And for me, this was the hardest and the most unknown part of the project. This is what I mean by saying reality was more real than anything I had imagined or dreamed or considered. And then we were even more cautious. We didn't want to just make the production engine the next engine. So we said, let's swap the shadow and the production. Maybe if we had run it longer, we would have found, but so we said, to be safe, we're going to do it. And then that was it. The new verified engine was the new production engine. And the reality changed from the old Java engine to the new Java engine. And so if you're like you can argue, you did all this work, all of this, for what? You're just essentially running the same logic. There's not much gained out of it, but there is. Now that we have a specification, and if we want to change something, we can have a new specification. We can connect those things with proof. And instead of just relying on code and fuzzing and shadow mode, we can prove the things about the two specification. And it means that the next reality, we will not need a quadrillion samples to deploy the next reality. As we move forward, we truly believe it opens a whole options. Like when I said we are getting started, like I truly believe that. This work was for us to get started on the innovation that we can do in this space. It allows us to be more nimble. Now, before I end, I want to talk a couple minutes about performance. We made a big deal, right? Like, oh, these versions, this string equals matcher. Does it have any impact? Did that have any impact? The other question is, how was the overall performance impact? And when we started, this is the pre-deployment graphs. The top one is the P99.9, which means it's the 0.1% slowest request that you see in the system. So you can see there's a lot of variance in there. And so we said, OK, we even had a chat with a bunch of principal engineers who had been working on the system for a long time. It's like, what is acceptable? Like, maybe we'll give you this fancy new formally verified tool. What's acceptable in a potential slowdown? And we never wrote this down on paper, but colloquially, they're like, OK, if you're 5% slower, that's fine. Try to keep it below 10%. If it's over 10, we got to talk. I'm like, OK, that sounds reasonable. So we deployed it. And here's all that garbage collection you're seeing. So that's the first answer, that your string matching matters. We were 65% faster. This was a massive result for the amount you can save in compute, in power, in customer experience. And why could we do it? We could do it because we had that insurance clause watching our back. The proof, we could do aggressive optimizations in things that people would not have even come close to touching because the ramifications, the impact, that wouldn't have been there. So while we started with a disjoint process, this was a hard road for us, saying like, how do we do it? Eventually, we were able to bring it together and have a way where the future cycle is not disjoint. It can live happily together. It can allow for these multiple evolutions in a way that is systematic. a question I've gotten asked, and this is what I want to leave folks on. Was this a feat of science or engineering? It's a question we talk about internally as well. And here's my take on this. It is a feat of engineering made possible by decades of science. Like, we didn't wake up one day and said, oh, we're going to prove this and build this compiler and do this fuzzing and do this other validation. This was it. This was like years and decades of the research folks have done in this room and others in our area across programming languages, verification, testing, software engineering that I believe has made this possible. So that's what made it possible. It made it possible to do these billion SMT queries a day. It made it possible to verify trillions of evaluations a day, the quadrillions sample. And for what's next, you know, come join AWS and find out. We are hiring for internships in 2025. We are hiring, there's multiple teams that are hiring full-time positions starting yesterday. And come make history with us. Thank you again for the kind invitation for giving this talk, and thank you all for listening.
Yeah.
Okay, good. Thank you. That was really inspiring, and I really like the whole cycle story with iteration and the big payoff in performance. So I kind of have an open-ended question. So I'm an academic who builds these tools, well, not as influential as Dafny, perhaps, but some of them, and I'm not at AWS. So what should be the takeaway for us, so who stay in academia and work on the tools that potentially might be used eventually?
So I think it depends on the research area, I would say, but one way to think about it is, and this is one of the things where it's like, for your tool or your technique, what is success look like for you? Like, is it a theoretical result? And, you know, often people say, oh, you know, industry doesn't use theoretical results. They use theoretical results that were like done 20 years ago. So part of it is, I really want to say to the broader community, there's no one size of success or impact. Like SMT solvers, they started way back when. Now they're to the point that we can use them. So I would say to anyone in academia, and this is not necessarily for you, like, push on what you believe in, whether if it's theory, whether it's tools, if it's tools, really try to find sets of examples where you are looking at scalability. Thinking about predictability in tools is a big thing. If you are, the other ways is for folks who are looking for more engagement, like, how do I know what's interesting in industry? Internships as well, but we also have, like Evan is one, like scholar positions where faculty can come part-time, spend their time at industry, sabbaticals, but this may not be a very satisfying answer, but really do what you believe and are passionate about, because that's the thing that's going to have impact, whether it's theory, practice, applied, all of those.
Thank you.
Neha's happy
Yeah, absolutely.
to answer more questions in the break. Let's thank the speaker again for a great talk.